So I don't know if you've noticed, but as we've been doing problems in this class, they're like really, really wordy type problems. And in every section we've done so far, it said something like, on the XY coordinate plane, blah, 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 blah. And you probably read right over that part. Well, the reason that all of the questions in this class have had to clarify that we're talking about a rectangular coordinate plane or an XY coordinate plane, which you're used to, is because it's not the only coordinate plane that we're going to be discussing in this class. This right here looks like a spider web, yeah? Mm-hmm. This is called the polar coordinate plane. So not only now will you be able to plot X and Y coordinates on a rectangular coordinate grid like you've been doing since middle school, we today are going to introduce how to plot points on what's called a polar coordinate plane or a polar coordinate system. A polar coordinate system is based on a grid of circles centered at the origin and on lines through the origin. Notice that these lines are all radians that we have measured throughout the unit circle. Polar coordinates, are defined as an ordered pair r comma theta, such that r represents the radius of the circle on which the point lies, and theta represents the measure of an angle in standard position whose terminal ray includes the point. In the polar coordinate system, the same point can be represented in many ways, because the r just basically tells me the radius, but what ring of circle I should put the point on, and the angle theta tells me the angle. So for example, and I'm going to use a lot of colors today to help us see this. If I'm plotting the coordinate point 4 comma pi over 2, I will first go to radius of 4. Everybody with their finger point at radius of 4. Hopefully you're pointing to the 4 on the positive x-axis, and now I want you to rotate it around until we're at pi over 2, which is the straight up and down line. The coordinate point of 4 comma pi over 2 should be right there. The ring labeled 4 for a radius of 4, and the angle being pi over 2. Do we see that? Okay, cool. Let's try. Yes. Okay, for the second coordinate point, 6 comma pi over 3. What is the radius that I'm using? 6. So I'm pointing at 6, and now I'm going to rotate. It's not the right word, but it's the right idea. I'm rotating to what angle? Pi over 3. So if I stay on the 6 circle and jump all the way to pi over 3, my coordinate point should be right there. I'm going to do that one in blue. 6 comma pi over 3. Now the next question gets really interesting. This says negative 8 comma pi over 4. Where should I start pointing my finger the first time for negative 8? The left side. So it is still a radius of 8, but it has been reflected. So we're starting at negative 8. From here, I want to move 1 pi over 4. I am not jumping back to pi over 4. I am going from the negative 8 and turning pi over 4, which means this is the coordinate point for negative 8 comma pi over 4. I'm making that one green. So negative 8 comma pi over 4 is right here, because we are pi over 4 radians from the negative 8 on the x-axis. Yes? For letter D, we're going 6 comma negative pi over 3. So where am I starting to point this one? 6 on the right, but it says negative pi over 3. So am I going the normal direction? No, I'm going to go the opposite direction. I'm only going to move a pi over 3. So it ends up being right here. 6 comma negative pi over 3 is the coordinate point right there.
So you would say it's like the closest?
What do you mean by closest?
So since in negative, like number C, like the radius is negative 8, we wouldn't do like we didn't go all the way back to the...
I see your question. Yes, by what you're meaning, yes, it's the closest because it only tells me to go 1 pi over 4. So I'm going to jump 1 pi over 4 to the next over 4. And same here, I'm going to go negative to the first pi over 3 since it says 1 pi over 3. If it had said negative 2 pi over 3, we would have gone 1, 2. Does that make sense? Okay, let's try the next one. I'm going to do this one in orange, in case you care about the color scheme. -2 comma pi over 6. Here's -2. And again, I'm only from there moving 1 pi over 6. So I'm going to the closest, I like that term, the closest pi over 6 because it's one of them. So my -2 comma pi over 6 would be here. That's the wrong color, Miss Quigley. There we go. And last but not least, we have our 1 comma pi. If we go to a radius of 1, it's really small in there. But how do I go to angle pi? Where is angle pi? I'm on angle 0 right now. If you mean by kind of on it, meaning it's all the way over here, I agree. This is 1 comma pi. Now what's interesting about all of these coordinate points is that we gave them a single address. And in the XY coordinate plane, there is only one address to get to like 5 comma 5. You go to the right 5, you go up 5. However, you've already seen that there's multiple ways for us to travel on this coordinate grid, correct? So what we're going to have to discover today is that there are more than one address to get to each point. This coordinate point right here was 6 comma pi over 3. It is also -6 comma -2 pi over 3. So there's more than one way to get to each of these coordinate points, which makes it very cool and kind of confusing. We will play with that later on in the lesson today. One of the main things, though, that I'm going to need us to do is to convert our coordinate points between polar, r comma theta, and rectangular, x comma y. And so we have a few coordinate points for you. Some of them look new and some of them are not new at all. Technically, this is a new way to write this, but if we are converting polar into rectangular, this is just the formula I've been having you write down on your formula chart anyways. That a coordinate point P is r cosine theta, comma r sine of theta, which is the x coordinate and the y coordinate. So if we use that right now and we're converting these polar coordinates into rectangular, all we have to do is the following. For 3 comma pi over 6 to find x, we would do x is equal to 3 times the cosine of pi over 6. Here's where knowing our unit circle is very important. What is the cosine of pi over 6? Square root of 3 over 2, correct? And so we have 3 times square root of 3 over 2, which means the x-coordinate here is 3 square root of 3 over 2. To find the y-coordinate, we would do 3 times the sine of pi over 6. What is the sine of pi over 6? 1 over 2. Which means that this is 3 over 2. My rectangular coordinate point is 3 square root 3 over 2, comma 3 over 2. I could plot this coordinate point on Desmos, and it would give me the same location if I was plotting the polar coordinate point 3 comma pi over 6. Which is pretty cool. Can I leave you to try the next two? Yeah. You have B and you have C. I want you to try to find me the rectangular coordinate points that are represented by those polar coordinates. All right, let's give this part B what? I don't even know what sentence I was trying to say. Let's give it a shot. There it is. For part B, I would do x equal to 4 times the cosine of 3 pi over 2, since that's r and theta. Well, the cosine of 3 pi over 2 is 0, which means the x-coordinate point is 0. And when I go to plug this in for the y-coordinate, the sine of 3 pi over 2 is -1, which means I should get the coordinate point 0, comma, -4. How did we do? Good on that one. Let's try the next one. If we have a radius of 2 and a theta of 3 pi over 4, we would just fill in that coordinate point. Hello, formula. 2 times the cosine of 3 pi over 4. Well, the cosine of pi over 4 is square root 2 over 2. And in that quadrant where 3 pi over 2 is, cosine is negative, which means we end up with negative square root 2 because the 2's cancel. And when we do this for y, the sine of 3 pi over 4 is also square root 2 over 2, but in that quadrant, sine is positive, so it's a positive version. So my coordinate point in the rectangular form is negative square root 2, comma, square root 2. Were we on the right track for that one?
Yeah.
I might have just not given you enough time to finish it.
Miss, how do we get like the 2 over 2?
How do we know that?
Yeah, how do you get it?
So in my head, what I do is I say cosine of 3 pi over 4 is like pi over 4. So I just do cosine of pi over 4, which is 2.
So it depends on.
The second type of conversion we're going to be doing today is converting from rectangular to polar. This one is a bit different.
So we're just.
To convert, when you are given a polar coordinate and you want the rectangular, this is the opposite. When you're given the rectangular and you want the polar, to find the radius, you're just doing Pythagorean theorem. Easy breezy, beautiful, cover girl. Okay, got it. When we're getting theta, we have to do multiple things. We have to, 1, do inverse tangent, which means we have to think about our unit circle backwards. And we have to remember that if we are using an x value that is negative, that whatever we get for inverse tangent of y over x, we have to add pi to it. So it gets a little complicated in this formula, but if you can have the formula in front of you, we can learn how to use it. For example, if the rectangular coordinate point I have is 3, negative 3, and I want to change that to polar, I know that this is x and that this is y. So to find the radius, I just do Pythagorean theorem. The square root of x squared plus y squared. And yes, you are going to have to do these without a calculator. What is 3 squared? 9. So we have 9, and then we have 9 again, because negative 3 squared is still 9. 9 plus 9 is 18. Now 18 is not a perfect square, so we have to break it down. 18 breaks down to 6 times 3, and 6 breaks down to 2 times 3. So that means it's 2 times 3 times 3, which means there's a pair of 3's and a leftover 2. I'm doing the tree in my head. We don't have space or time to break down 18 with the tree. It is 2 times 6. 6 is 2 times 3. So it's 3 times 3 times 2. Okay. Cool. That's our r coordinate. Now we need theta. Theta is found by doing inverse tangent of the y divided by the x. The x value here is a positive 3, so I don't need to add pi to this answer. Only when the x is negative do you do plus pi at the end. Well, my friends, what is negative 3 over 3? Negative 1. So now we just have to think about inverse tangent. How can inverse tangent be equal to negative 1? Well, when is tangent equal to 1? Where is it the fingers below and the fingers above the same? Pi over 4, but we want it to be negative, so that means that this is simply negative pi over 4. We go back to our abilities to do inverse tangent, to read our unit circle backwards. So our coordinate point here, our polar coordinate, is a radius of 3 square root 2 and a theta of negative pi over 4. If we do the second one together before you try the next one, this one says that we have the x and y coordinate negative 3, square root 3. Okay. So I know that I'm finding the radius by doing Pythagorean theorem. So this is negative 3 squared plus square root of 3 squared. Well, you guys already told me that negative 3 squared is 9. And the square root of 3 squared is just 3. The square root and square cancel each other out. So that's 12. But can we break down the number 12? How does 12 break down? 6 times 2. 2 times 3. So in total, that's 2 times 2 times 3, which this means a pair of 2's and a leftover 3. If you need to make the tree, go for it. We're trying to get past those rudimentary skills. Yes?
I know you said you weren't going to write it out
Yes. This is what I'm doing in my head. Y'all remember doing these trees?
Yeah. Oh, okay. Yeah.
That's what I'm doing in my head. Now we go to the theta. We know theta is going to be the inverse tangent of the y divided by the x. But my spidey senses need to go off because what is different about x in this problem? It's negative, which means at the very end I have to add pi because x is negative. Y can be negative all at once. If x is negative, you add pi. Okay, we have to think about it. How is tangent, or when, what angle makes tangent equal to square root 3 over 3? Think about your table. You wrote it down on your formula chart today. Pi over 6, but if we want the negative version, how do I answer that? Negative pi over 6. Now, unfortunately, I need to add pi to that. To add fractions, what do they both have to have? Cool, here's the common denominator. 6 over 6. So negative pi over 6 plus 6 over 6 means that my theta would be equal to positive 5 over 6. Sorry, positive 5 pi over 6. So my coordinate point is a radius of 2 square root of 3, comma, 5 pi over 6. Are you ready to try one on your own? Maybe. I like the spirit. Let's try it. Let me get you past this first hurdle that I can tell everybody's stuck at. So for the radius here, we did square root of negative 4 squared plus negative 4 square root of 3 squared. I am assuming that the reason you're asking me questions is because we're like, okay, well, this is clearly 16, but how do I do that part? 48. It is 48. So we will square this part, which 4 squared is 16, and then square root of 3 squared is just 3. So we do 16 times 3, which, yes, I expect you to be able to do in your head, is 48. Can I leave you here?
Yes.
Great. I'm going to fast forward us even if you're not finished. So when you add these together, what do you get?
64.
And what is the square root of 64? 8. Nice. If we go to find theta, I know that I have to do inverse tangent of y over x. And since that x is negative, I add pi. Well, negative 4 over negative 4, what does that reduce to? 1. So I'm really just doing the tangent of square root 3. Sorry, inverse tangent of square root 3. What's the angle that gives me square root 3 when I take the tangent of it? Think about your table.
It's on the top. It's in the middle. Is it pi over?
Not 6, not 4. It's pi over 3. So this becomes pi over 3 plus pi. But to make them have the same denominator, I'm just going to make this 3 over 3. Which means my angle is 4 pi over 3. So it's 8 comma 4 pi over 3. Now there's a bit more when it comes to these polar coordinate points, but we're going to stop there because I really want to make sure that we understand how to find the address of these coordinate points, the r and the theta. Your homework will have more practice on converting them back and forth, but we're going to practice with a little activity.